We learned that we can represent the bonding and lone pairs of electrons in a molecule by a thing called a Lewis structure. We also know we can use electronegativity difference to work out if the bonding in those molecules is polar or non-polar. So it creates a dipole in the bond. What we're going to look at now is how we can use a thing called the VSEPR theory to work out the shape of the molecule, and then that will help us predict whether it's a polar molecule or not. The reason that polarity is important is to do with some more properties, such as melting points and boiling points, and being a little bit higher than we'd expect, and solubility in water. Polar things dissolve in water, non-polar things don't, for example. Okay, so what is this VSEPR thing? Well, it's actually a really nice answer in an exam, okay, for explaining why certain things are a certain shape. It stands for valence shell electron pair repulsion theory. So it's about the valence shell electrons. It's about the fact that they exist in pairs, which we show using a Lewis structure anyway. And because electrons are negatively charged, they repel each other. So they try to get as far away from each other as possible. So you can break this down quite nicely. I'm only looking at the valence shell electrons, the ones we show in a Lewis structure. I'm showing them in pairs because that's how electrons exist to make chemical bonds, or when they are lone pairs. We'll get to that in a moment. And the fact that any regions of electrons will repel, so stay away from each other as much as possible. And that's why we've got some marshmallows and toothpicks and stuff, because we're going to try and show how this would work. So, because it's looking at the valence shell electrons, often a good thing to do is to start with a Lewis structure. So I'm going to first of all look at CH2O. Carbon is the thing with the highest valency there, so it will be my central atom. So I'm going to be looking at the shape of this molecule around carbon. I don't care about the shape around the other atoms, it's just the central atom that I care about. So I'm going to put my carbon here. Doing its Lewis structure, I end up with this. I might have had those in a straight line, perhaps, and that would be equally correct, or one up and one across. So I end up with this as my Lewis structure. Now what I'm really looking for here is how many regions of electron density is it? So regions that are repelling each other around the central atom. And I can see that I've got, around the central atom, a single bond, and a double bond. We class this as 3 regions of electron density. There's a lot of electrons in a small amount of space there. That's what a chemical bond is. It's a pair of electrons very, very close together, creating a relationship between these two nuclei. So we call these regions of electron density. This has got 3 of them. 3 regions of electron density. And that's how we phrase it if we're trying to explain it. Each of those has got an atom at the end of it. So each atom helps make the shape of this. So what we're going to do shortly is we're going to get our marshmallow. We're going to put 3 toothpicks into it and put them as far apart from each other as we can. And we're going to estimate the bond angle that we create. And what we're going to find is that the best way is to have them sitting as a flat triangle. Okay, to have them sitting as a flat triangle. If you were to move one up or down, you end up closing some of the angles in, so it doesn't work. So each of these atoms contributes to the shape. These electron density areas try to get as far away from each other as possible. And we're going to find that they create, in this case, a 120-degree angle. Because it's going to be a flat triangle. Because there's something on each end, so I've got an atom here, the central atom here, an atom here, and an atom here, the shape it's made is a triangle. And it's a triangle that sits flat, so we call it triangular because it's a triangle shape, planar because it sits on a flat plane, on a bit of paper or on a whiteboard. This gets a little bit more complicated though when we look at something like water. So I'm going to get rid of the carbon and make it H2O now. Okay, and you'll see that something different happens. If I draw H2O and I do its lowest structure, I often end up with it looking something like this. Those two might be opposite each other or up and down, it doesn't matter, but that's roughly the lowest structure I'm going to get. Now here, I've actually got 4 regions of electron density because it says pairs here. Well, there's an electron pair, so that is a region of electron density. So I've got 1, 2, 3, 4 regions of electron density, because lone pairs count as one region of electron density. So a chemical bond is a region of electron density, and a lone pair is a region of electron density. So this has got more of them. Now, one of the tasks I'm going to get you to do later with your toothpicks and your marshmallows is get 4 toothpicks as far away from each other as possible. And I'll give you a wee hint, it's not going to sit flat. We're looking in 3 dimensions here. If you were to do a square, where they're all one sticking up, one down, one left and one right, you're going to end up being able to manipulate that so they actually are further away from each other than 90 degrees. So in 3 dimensions it doesn't do that. So what we end up finding happening is if I've got my central atom here, sorry, I've got to do the bonds here. If I've got my central atom here, when I get this done perfectly, it creates what's called a tetrahedron, which isn't a surprise. Tetra means 4, so 4-sided, and the hedron bit means it's a shape where all the sides are the same. So it makes a 4-sided shape where all shapes are the same size. So it's not a cube because cubes have got 6 sides. Okay. So if I had one going straight up here, I would expect another one to go straight down the bottom. But actually a tetrahedron has one sticking out here on an angle. If I have those two sitting on the same plane, I find one is sticking out at me like this. So I represent that with a triangle, which is meant to show the bond coming out of the page at me. And then what I notice is there's another one going into the board on about the same angle directly behind it. That makes it pretty hard to draw as well. So what we do generally is we'll move this one over, which is a little bit incorrect for the bond angle, but it'll do for now. And we show the one going into the board there as a series of dashed lines that get smaller and smaller going down to a point. If I look at water, sorry, I've skipped a step, then when we have a look at this, we find the bond angle here, if I've got it perfectly symmetrical in 3 dimensions, is about 107 degrees. It's a little bit more. It's 107.5, but 107 degrees is all you need for this year. Okay? It's 107.5 if I round it off to the nearest half. Then I look, how many atoms have I got bound to this? And I've only got 2. And the way I've drawn it, it would be here and here. These lone pairs don't count for the shape, they only count for the bond angle, because lone pairs repel. So the 4 regions of electron density repel each other, but I've only got 2 bonded atoms. So this shape, if I was to spin it around, is like the letter V. So not surprisingly, we call it V-shaped. You will also see it called bent, and you will also see it called angular, because it's on an angle. Okay, 3 things joined together by an angle. All 3 of these are accepted as answers if you're doing this in NCEA level 2 and in level 3, by the way. So these are all acceptable names for this, where I've got 3 things and it's bent. It's bent because of the bond angle here. The bond angle is created by having 4 regions of electron density. Okay? In our task that we're going to do today, we're going to use our marshmallows and our toothpicks to find out what the bond angles would be when we have 2 regions of electron density, 3, and 4. So we're going to try and confirm this. We're also going to have a look at what shapes are made depending on how many atoms are bound. So if I've got, for example, 3 regions of electron density, but actually only 2 atoms bound to it, let's say that hydrogen wasn't there, let's say it was a lone pair, then what shape would that be, do you think? If it was just those 2. What letter is it like if you tip it up? V, well done. So it's the same. Same name, different bond angle though, because the bond angle would still be 120 degrees. 120 because it has 3 regions. 107 because it has 4 regions. Guess what it is for 2? 180. Perfect. So you've only got one shape possible there, haven't you? What would a straight line be called if you want to use a fancy sciencey or mathy type name? Linear. Well done. Cool. Okay. The only other real difficult shape is, what if I had one here? What shape's that just made?
Triangle.
But it's up. Someone said it.
Triangle.
Good. It's a triangle-based pyramid. So we call it, rather than triangular planar, we call it triangular pyramidal. It's actually a pyramid. If I put one there, it's made a triangle-based pyramid. All right. You learn a whole lot more of them in level 3. There's a heap more because lots of atoms actually do break the octet rule. But we'll get to those next year.